Yeah, okay. It's a pleasure to have Professor Micklitz here today to talk to us. Professor Micklitz did his bachelor's and got his PhD in 2007 at Cologne University in Germany. He did two postdocs, one from 2007 to 2009 at Argonne National Lab in USA, and another postdoc from 2009 to 2013 at the Free University of Berlin. And since 2013, he is at Centro Brasileiro de Pesquisas Físicas in Rio de Janeiro. And today, Professor Micklitz is going to talk to us about the dynamics of the measured SYK model, which is very interesting for me because maybe I will finally understand what is the SYK model, which I have seen around and I never understood. And I failed to mention that Professor Outland was your advisor, right? And I think that Professor Outland has done a lot of work in the SYK model too, right?
Right, yes.
Was he the one who developed the model or not?
No, actually, I mean, this model is quite popular right now, but it's actually has a long history, right? It's like a random matrix for interacting systems. So it has a long history. So I try to put my point of view of the model here in this talk, yeah.
Okay, so thank you very much for accepting our invitation, and the microphone is yours.
Okay, so thanks a lot for the invitation. So it's a pleasure to speak here. And so I report on some attempts that we made lately to try to understand the dynamics of the measured SYK model. And this work is done in collaboration with the Cologne group. So it involves Michael Buchholz, Sebastian Dien, and Alex Aldan from Cologne. And yeah, so I'm going to start with a brief motivation for the topic. Then actually, I mean, at least for me, it's quite interesting because we are seeing all these ideas, quantum information entering condensed matter physics. So at least for me, it's sometimes hard to understand these concepts. And specifically in this project, I had to learn a little bit more about measurements. So I included a brief excursion about projective and continuous measurements, which I found interesting, and I hope you'll also find interesting. And then I come to our work on the dynamics of the SYK model. So let me start out with a brief motivation. So well, in the recent years, we have witnessed quite a lot of progress in the manipulation and control of closed many-body systems. And I think one very interesting question that there often pops up is about the ergodicity in such closed many-body systems. That is, understand the conditions and under which system such closed many-body systems are ergodic, or under which cases breaking of ergodicity happens. And this, I think, is a question of theoretical interest, but of course it's also of practical relevance. So for example, here, for more than 50 qubits in this IBM computer, so there are nonlinear coupled transmons. You don't want them to operate in a chaotic regime, right? Because then there would be no possibility to store information, because the chaotic dynamics would just erase any possibility for information storage. So it's also not only a question of theoretical, but also of practical interest. So just a very brief slide on ergodicity breaking. So I think, like in classical systems, we can at least visualize very nicely what ergodicity means. So here shown in the first line, just the phase space of 1D classical system that is driven. So it's actually a particle moving on a ring, which is periodically kicked. And the kicking is nonlinear coupled to the coordinate of the particle. So this will, for strong kicking strengths, create chaotic dynamics, which is here seen on the very left, where a trajectory just uniformly fills phase space. So this is what we understand under ergodicity. And as the kicking strength is reduced, we see here already some stable islands forming. And then for very weak kicking strengths, we have an integrable system. So this is in classical system. Quantum systems, the notions of ergodicity and chaos are a little bit more involved. So usually what people do is they talk about signatures of chaos, for example, in quantum systems. And what is usually identified with this is that the properties, the statistical properties of your Hamilton operator are the same as that of random matrices. So the analysis of level correlations and wave function statistics is then a usual method to detect or to compare this to random matrix theory predictions to see what is if a system is in a chaotic regime. Now there is also other ways. For example, one can identify ergodicity in some cases with the eigenstate thermalization hypothesis, and maybe a more information-based approach would be to say that chaotic systems are information scramblers. So what it means is that information is spread over all degrees of freedom in a very complicated way, such that it's not easy to recuperate the information in local measurements. So okay, so in the integrable, like in the ergodicity breaking side, so typically what happens there is that quantum state can keep the memory, so this allows you to store information, and often this is related then, so the transition into a non-ergodic phase or regime is related to the appearance of conservation laws in integrable dynamics. So this is also the case in the Medi-by delocalization problem, which has been studied a lot in the last years. And this is here showing just the prototypical Hamiltonian for a Medi-by delocalization problem. This is a 1D coupled spin chain, nearest neighbor coupling here with some random coefficients. So this contribution to the Hamiltonian will generate the many-body chaos. And then to counteract the many-body chaos, one can introduce usually some potential. So here, this is in form of a random magnetic field. So this is a random magnetic field on every side. And as the this order strength or the strength of this random magnetic field is increased, one can make a transition from a thermal phase where the system is fully chaotic, so thermal, and the system is its own bath. One can make a quantum phase transition into a non-equilibrium phase where the system is not its own bath anymore. And actually this transition is a little bit maybe unconventional because it does not always only involve the limit, the thermodynamic limit and sending to infinity, but to actually detect it, one cannot see any signatures of this transition in thermodynamic quantities. So typically what one can look at is at time resolved correlation function, then this limit, the one also has to imply a limit where time is sent to infinity. So as already mentioned, or traditional indicators for the ergodicity to non-ergodic transition or the many-body localization transition is the statistics of levels and wave functions. So in the chaotic or the ergodic regime, this statistics should coincide with predictions from random matrix theory, and deviations from that can then be identified with the breaking of ergodicity. But there's also more, let's say, information-based concepts like the entanglement entropy. So in the thermal phase, the entanglement entropy of generic eigenstates follows a volume law. And once one makes the transition into the non-ergodic phase, this volume law is changed into an area law. And this can be actually stated in a different way, saying that the information stored in generic eigenstates in the thermal phase is vanishingly small or goes to zero, while it becomes finite in the non-equilibrium phase, in the non-ergodic phase. And here the information stored is simply the difference between the entanglement entropy and the thermodynamic entropy of a fully mixed state. One can then, of course, ask if there's other variants or realization of such an, let's say, entanglement transition if this can be realized in other contexts. And one thing that has been discussed quite a lot recently is the idea to make such an entanglement transition via measurement. So the idea is that then the chaotic information erasures that you have in the ergodic regime or relate to the many-body chaos is counteracted for by information gain through quantum measurements. And there's two models which I briefly mentioned here, which are reasonably well understood. And this is on the one hand the random unitary circuit and the 1D free fermion. So in the random unitary circuit, what you have is these vertical lines here would correspond to some local Hilbert space. So it can be, in the simplest case, just 2 dimensions. So it's a spin 1/2. You can have spin up or down. And then you have, so you have here a 1D system with these, let's say, spin 1/2 particles. And then what you do is you generate dynamics by applying unitary operations. So you do this in the following way. So first, you always apply random qubit operations on neighbors, which will entangle these two spins. And then you do the same, but now altering the neighbors. So you do this in this brick fashion here, shown by these green boxes. And this will then entangle in time all the local degrees of freedom. And this way, this dynamics itself would generate many-body chaos. And now this is counteracted for by doing local measurements. This is the blue dots here, or the circles here. They indicate local measurements that are done with a probability P. And then the system can be nicely, for example, simulated. You see that the probability for the local measurements is increased. One makes a transition from a volume law of the entanglement entropy, which would correspond to the ergodic regime, to an area law, which would correspond now to the non-ergodic regime induced by the measurements. Now, in the 1D free fermions, it's a little bit different. So in the 1D free fermions, well, we do not have many-body chaos. And then the transition that happens here is at weak measurement, one has a log entanglement entropy that crosses or then makes a transition into an area law at strong measurement. And in the case of free fermions, it's well understood that this transition is related to a Kosterlitz-Thouless transition. Now, in case of this random unitary circuits, it's more complicated. However, there's one limit that is very well understood. That is when the dimension of this local Hilbert space goes to infinity, then it's understood that this transition is of percolation type. Now, there is one thing I think which we learned from many-body localization during the last years, which is that special attention has to be paid to mesoscopic size systems. So what we learned from many-body localization that, of course, in any finite system, you don't have a two-phase transition, but it's a crossover, but you can try to find the critical strengths at which then this takes place from a finite size scaling. And what we learned, at least from many-body localization, is that this can be a very tricky affair because in the many-body localization problem, the critical strengths at which you would say the transition occurs from finite size scaling, the critical strength has quite a substantial drift as you increase the system size. So this is something well understood by now, but which has created quite some discussions. And this makes this problem in a way complicated, but also interesting, because this means that in any finite size system, we would from, let's say, these finite size scaling analysis detect or predict some transition net and interaction strengths that can be well separated from the actual transition that would take place in the thermodynamic limit. And we have this intermediate regime, which is dominated, let's say, by precursor effects of many-body localization, which is now called also sometimes called pre-thermal. So we have quite some interesting physics going on there. And this is in a way our motivation then to try and study the measurement-induced dynamics in a many-body chaotic systems that is of mesoscopic size. So we want to talk about a system that has a large number n of degrees of freedoms, however, that it's finite. And here comes now my introduction to the SYK model, at least from my point of view. So hopefully this is useful for George. So that's the way at least I would see it. So if you talk about these mesoscopic sized many-body chaotic systems, you can start first looking at the single particle contribution to the Hamiltonian. Now, the main observation here is that if you have a lot of degrees of freedom, the system is, or dynamics is typically complex enough such that the single particle dynamics of the system is chaotic. So you have extended single particle states, which can be modeled, for example, by random waves using like the idea of Berry, right? So you have random waves that are the eigenstates of a single particle Hamiltonian. Then introducing interaction term, you can see that expanding the matrix element of your interaction in terms of these random waves, you will generically generate such an interaction term where you now have all-to-all interaction with a random coupling. And this, then the combination of such a random 2-fermion and a random 4-fermion Hamiltonian can then be viewed as, let's say, a universal Hamiltonian of mesoscopic sized system. So this is all still here about complex fermions. And now comes the thing in the SYK model that is, we want to take a model, at least in our study, which is, let's say, the most entropic, or which in our case is the most information scrambling. So we want to eliminate all the conservation laws. And that can be simply done by passing from complex fermion to real fermions. And that's just like how at least we see our model. We just eliminate all the conservation laws. So we take here a model of with a random 2 Majorana fermion and a random 4 Majorana fermion contribution, and that's the SYK model that we talk about, SYK 4 plus 2. And then the measurement will be done here by measuring the occupation of local occupation of the complex fermions. Now, actually, what we more precisely do is we convinced ourselves that at least the measured dynamics is completely insensitive to this 2 Majorana contribution. I mean, we know that this for other quantities that's more subtle, that can introduce, so without this 2 Majorana, you have a non-Fermi liquid, and this makes then a transition to the Fermi liquid. But all this doesn't play any role for the measured dynamics, so we verified this in our simulations, and that's why throughout most of the talk I will just forget about this term and talk only about the random 4 Majorana. Now, there's actually a nice way, I think, to think about this Hamiltonian, and that's a picture that I also use throughout this talk, and this is to think about how this Hamiltonian acts on the Fock space of your complex fermion. So you have a 2 to the n-dimensional Fock space, which just corresponds to your n orbitals being occupied or not occupied. So you can visualize a generic state of your fermion system as, if you like, also as an n spin system, where spin pointing up corresponds to occupying this single particle orbital and spin down to not occupying it. So one specific configuration, one specific state of this Fock space would correspond to this n spin configuration. And then you can think how now this Hamiltonian acts on these beta states. And then, well, you just have to recall that the Majorana fermion is a linear combination of a creation and annihilation operator, which means that acting with such a contribution in the SYK 4 Hamiltonian, for example, means you just pick 4 of these spins and then you invert their orientation. So, or you invert the occupation of your single particle orbitals. And this is just then weighted with a random number. So in this picture, we can think about this n spins, which are then flipped. So you pick 4 of them and you flip 4 of these spins, weighting it with a random number, and this will then generate the chaotic dynamics of this mesoscopic systems. Now, what counteracts this let's say information scrambling dynamics is that you always locally then measure your spins, so you gain information by locally measuring whether spin is in spin up and spin down state. So this actually then brings me to how exactly the measurements will be done. So that's my brief excursion on projective and continuous measurements, which I found interesting. So, and actually this is a little bit a busy slide, but I'll just come to the main point, which is at least like how I always thought about measurement, and this is probably how everyone learns it just in the quantum mechanics course, is that you have measurement represented by some Hermitian operator, and so you can think about the eigenstates of this operator, and what a measurement does, it just projects your state you start out with. So the measurement after measurement, you will have projected your state onto an eigenstate of your measurement operator, which implies that after this projective or von Neumann measurement, you actually have complete information about the state you're in after measurement. So this is also what the collapse of the wave function says. So after the measurement is described by the projection of your state with this onto the eigenstate of the measurement operator, and this then has to be normalized by dividing by the square root of the probability to actually find this eigenvalue of corresponding to the eigenstate, and this probability is given by this matrix element by the Born probability. So what I didn't know is that there, or I heard about it, but I never really understood is that there's generalization to this kind of projective measurements, and these are then measurements that generalize the projective measurements, and the idea is that after the measurement, by the measurement, you only extract partial information, and the idea is that you can introduce what is called positive operator valued measures, so that's the POVMs, which satisfy nearly all the usual properties of your projection operators. But there's one difference, which is exactly defining what a projection is, that the square of the operator reproduces itself. So you give up this one condition, but apart from that, you can define then the set of positive semi operators, which also spans the unit operator in Fox or Hilbert space, and you can define in the same way a collapse of the wave function. But the difference is that you only extract partial information, so after the measurement you don't have complete information about the state. And to illustrate this, one can look at a simple example of a particle, let's say, moving on the real line. So in this case, one can think about a basis as just the coordinate states, and one can cook up such a POVM by taking a linear combination on projections onto certain coordinates on this line. And this linear combination here in this case is given by convolution with some, or no, by some multiplication, some over some Gaussian function. So in case where the width of the Gaussian goes to 0, well, then this is just a projection onto a single coordinate, and one is back to the projective measurement. However, when for example, in the opposite extreme case where the width goes to infinity, this would be just a unit operator, so you wouldn't gain any information. And if the width is in some sense large, then one speaks about weak measurements. And actually, there's another, I think, quite nice way to think about these POVMs. And that
Tobias, may I ask a question about the last part of the previous slide?
Yes.
Do you require to describe these POVMs that you use in non-square integrable basis? Because the X basis is not. No. No.
You can do it with spin also. Yeah.
Okay. Yeah. Thank you.
So there's I think a nice way to think about these POVMs, generalization of projection operators, and that's actually in a way the same relation as between mixed and pure state. So we understand that we can always understand the mixed state of some system A as a state as resulting from a pure state of a larger system where we just traced out the environment. So we can think about a mixed state in system A by coupling the system to an environment. Then we have a pure state in the overall system, and tracing out the environment, one has then the mixed state. So in the same way, we can think of as these POVMs as resulting from projective measurements in an enlarged system. And to illustrate this on the example of the previous slide, so we can think about our POVM on the real line, which was just discussed on the previous slide. And then what one can do is one can always introduce some projective measurement on a larger system that will reproduce this. So for this specific example, what one can do is one can make a copy of the original system. So take another real line, system B now, which is usually called the ancilla. And then what one can do is one can start out from some specific let's say product state, and entangle then the two subsystems by some unitary operator. And then one can do a projective measurement on the ancilla, which will then produce exactly this POVM on the original system. So we can always understand these POVMs as projective measurements on a larger system. And the important information, or the important part here, is that, as said, these POVMs then only extract partial information, so the measurement reduces uncertainty on average, but does not remove it completely. And actually, one nice thing about this, and this is what we'll use in the last part of the talk, is that for these POVMs, you can then come up with a dynamical equation which describes how the measurement affects your wave function. So you have something which is called the stochastic Schrödinger equation, which describes the dynamics of the measurement. And the idea is as follows. So you apply now your measurements always at every time interval delta t, and you do the measurement with a weak measurement, where the measurement strength itself also scales with the delta t. So then you have a well-defined limit sending delta t to 0, where you more and more off measure but get less and less information. And this limit you can come up with some differential equation that then describes the change induced in the quantum state by weak measurement, and this is known as the stochastic Schrödinger equation. So this has here two, I would say, characteristic ingredients, which on the one hand is this phi of t, which is some random measurement noise, it's called. So that takes into account that the measurement outcome is random, and what one then typically does is, so one can, let's say, dice out certain sequences of these outcomes, phi of t, which will then give you a measurement record along time. And then you can solve this stochastic Schrödinger equation conditioned by these measurement records. So this you can evolve the state along these outcomes, and this would then generate you what is called the quantum trajectory. But of course, you can have, if you want to talk about average quantities later on, you should average over possible outcomes and average over these quantum trajectories. Now, there's a second ingredient in this stochastic Schrödinger equation, which actually describes unitary evolution now, which is that there the measurement operator, that in this case would be just a position operator, always comes in the combination with the expectation value of the measurement operator. And this expectation value is now the expectation value with respect to the instantaneous wave function. And that makes the problem very hard, because this means you have some nonlinear feedback of the wave function to this equation, and this makes it quite a complicated problem. Now, the stochastic Schrödinger equation, as said, describes the state evolution conditioned by the measurement outcomes. And one can convince oneself that this actually describes, so if you only have measurement, describes the progressive collapse as information is accumulated. So instead of having like the projective measurement, the immediate collapse, if you only look at this stochastic Schrödinger equation, it will just describe your progressive collapse, meaning that the stationary state that is finally achieved is a state that is just an eigenstate of the measurement operator. And now this then brings us to the problem what we want to do. So we want to study now the dynamics of this maximally information scrambler in a mesoscopic system, which I argued is given by the SYK model. And so we have this information scrambling dynamics, and then we have these measurements which will always gain information, counteract this for. And as I said, it's convenient to think about this problem in terms of the spins, where the many-body chaos induced by the all-to-all spin flips between four spins, and the measurement is the local measurement of the spin, where we gain information. Now, what we use for an observable to detect the dynamics.
Tobias, just a question. You are doing measurement in a single spin, a number of spins, always spins, or it doesn't matter?
No, just a single spin. It's always
single spin.
A single spin you measure, and then yeah.
It's always the same spin.
No. Oh, sorry. So you randomly choose a spin which you then measure.
Okay.
Right. So
okay.
Yeah, actually, I'll come to this. So we use in the beginning we use phenomenological approach, then we use projective measurements, in the end continuous measurement. I think it's the most clear maybe in the projective measurement, but it's always like you measure like this. I mean, the continuous measurement, you always measure continuously, right? But at least in the projective measurements, we take a single spin that we then measure, right? Mm-hmm.
Okay.
And the observable that we use is what is called the purity. So that's the trace of the density matrix squared. So we start out from a state that doesn't contain any information. So the maximally mixed state, just the unit operator, the density matrix being the unit operator in Fock space. So again, D here is 2 to the n, the Fock space dimension. And then what we look at the time evolution of this density matrix, then we take the square of the density matrix and take the trace of it. Just taking the trace of rho, I mean, wouldn't change anything, it wouldn't find anything. So you have to go to higher moments of the density matrix to detect this, let's say, purification dynamics. In the simplest case, it's just looking at the second moment. One could also look at von Neumann entropies and so on. But we here look at the simplest case, which is the purity second moment. And just maybe one thing two simple cases one should have in mind. So if one has only the information scrambling dynamics, so you start off from a maximum mixed state, which doesn't contain information, and the chaotic dynamics wouldn't change it. So if you plug this here in, the square of the density matrix is then 1 over d squared times the unit matrix. So taking the trace gives you a factor d. So you would have a purity which is exponentially small in the number of degree of freedom. So it's 1 over d. On the other hand, if you just start out with the state, but you only do the measurements, then we know that you will in the end purify your system. So you will end up in an eigenstate of your measurement operator, meaning that rho squared is the same as rho, meaning that the trace is 1. So that's two limits that we should have in mind. And one can visualize this maybe here, like this would be now the absolute value of the density matrix elements in a basis that is the eigenbasis of your measurement operator. So we start out from the completely structureless state, which is diagonal and the same in all elements. So that's the unit matrix. And then if the purification dominates, we expect that this will evolve into one specific eigenstate of the measurement operator. So there will be just one peak in this case. So okay, so this then brings me to our attempts to try and understand the dynamics of the measured SYK model, and maybe it becomes clear during the talk. It's I don't know if it becomes clear, but we first thought it's an easier problem. We had to learn that it's not as easy as we thought in the beginning. So that's why we use different approaches to try to understand what is going on. So we have our Hamiltonian. Now, this is the SYK Hamiltonian, which introduces many-body chaos, which has a coupling constant, which we call J. And then we have a measurement, which is parameterized by a measuring rate, which is eta. And then what we did is we looked at, we applied 3 different approaches to try and understand the dynamics. So in the first case, we looked at the strong measurement limit. So where the measurement rate is much larger than the strength of the many-body chaotic Hamiltonian. And it turns out that actually this is the simplest case to understand. There is a simple, let's say, phenomenological model by which we can understand quite well what is going on. Then in the weak measurement, it's actually more complicated to see how the dynamics occurs in this mesoscopic system. And here we use then a continuous, we use projective idea based on projective measurements in this limit, and I'll discuss this in a bit more detail. And finally, what we did, so we got some insight from these 2 limits from our analysis, and then just looked numerically what happens for more moderate ratios of eta to j, and found that these characteristics that we find in the strong and weak measurement limits are quite robust. This then led us to try and understand still how the transition between these regimes is taking place, which then uses an effective Hamiltonian description, which is based on the stochastic Schrödinger equation with continuous measurements discussed. So as already said, but maybe I repeat again, so there's actually 2 simple limits, which is in the one case where we do not have any measurements. We start out from the maximal mixed state that will stay a maximal mixed state. So the purity is just given by 1 over d, exponentially small for all times, also in limit t to infinity. In the other case, if we start out with the maximum mixed state, we start out with a state that has purity exponentially small, but since we only measure and there's no scrambling, this will evolve into an eigenstate of the measurement operator, meaning that in the long time limit, this should purify and take the value 1. Okay, so then going to the strong measurement limit first. So we assume that the measurement rate is much, much larger than the interaction strength of the many-body chaotic system. And actually, we go to a limit where we say, okay, let's go to the simplest limit and just forget all the information scrambling that is happening in between the measurements, because the system doesn't have enough time to fully evolve ergodicity. In this case, we do now bold assumption. Well, let's forget first about all the chaotic dynamics and just look at the dynamics induced by the measurement itself. In this case, the problem simplifies considerably because the purity for our n-spin system then factorizes just in the power n of a single qubit purity. And then one can just make the assumption or observe that actually the probability that no measurement has been done or taken place after time t is a Poisson process to identify the probability to not having made a measurement after time t, just as the exponential where the measurement rate is multiplied with the time. And with this, then one can figure out what is the purity, the purification, or what is the purity of a single spin, and taking the power n of this, we arrive at this result here, which are the solid lines. And we see that this very nicely actually describes our simulations of the SYK, measured SYK models for small ratios where the coupling constant of the SYK model is 100th, let's say, of the measurement rate. So this works quite well. And the important information here then is that the typical or the characteristic timescale on which purification is reached is growing logarithmically in the number of particles. And this is actually showing here in the inset, where we see how the purity approaches 1 in the long time limit, and it follows nicely this prediction. And the typical timescale, as said, is logarithmically growing with the system size. Now, in the opposite limit, it's more complicated. So let's go to a limit where actually the measurement rate is very small, much smaller than the typical time scale, the typical energy scale for the many-body chaotic system. So we have, in a way, always, okay, and now here we are doing, for simplicity, or I think it's more simpler to consider the projective measurements. So we do projective measurements every time 1 over eta, where we gain an information log 2. But in between, we leave enough time such that, so the typical time scale on which ergodicity is reached in this SYK model is given by 1 over j, and we look at time scales much larger, so we leave the system enough time to fully scramble the information over the entire Hilbert space. And then we can try to answer the question, well, how is this fraction that is always obtained in the measurements, how is this retained in the finite system, and how if there is a purified state reached in the end? And to address this now, we make a calculation which actually has one uncontrolled approximation, which we could do better. But okay, let me here briefly go a little bit into detail. So the idea is that we look at the density matrix after L projective measurements have been made. So we start out with our initial state, which is just the maximic state. We make a projective measurement. So we measure one single spin of the n spins. Then we make the unitary time evolution, which now, since we leave enough time, is the evolution of a fully scrambling evolution dynamics. So we model this now just by a d times d dimensional unitary matrix, which is just randomly drawn from the Haar distribution, Haar measure. So this would be like the perfect information scrambler. Then again, we apply a local measurement of a different spin or the same spin, like a randomly chosen spin, and so on and so on. So we repeat this L times and arrive in this way at the density matrix after L measurements. And well, this now would be a density matrix that is not normalized because we have all here this projection operation. We do not do the normalization. So we have to, in a way, separate the normalization then, which is just a trace of this density matrix. So with this, we can then calculate the purity after L time steps as calculating the average now over all these random unitaries of the normalization factor squared times trace of this not normalized density matrix squared. And then there comes the one approximation that we just do because we do not know how to do it better, but hopefully this gets qualitative things right. And I think it does, so I'll discuss this, which is that in this average, we assume statistical independence of the unitaries that enter the normalization factor in the unnormalized density matrix. So that's one step we have to do. But if we do this, then at least we can nicely solve this problem. And the observation is that, well, you have two invariants under this, let's say, average, which is the trace of the unnormalized density matrix, so the trace squared also, or the trace of the unnormalized density matrix squared. So these are the two invariants, and you can write down some transfer matrix equation which relates these two quantities after L-1 measurements and L measurements, and this matrix that connects these two invariants can be calculated from these averages over unitary matrices. And what you arrive at using this idea then is a purity which is given by this expression. And there's one crucial finding, which is that, well, we find from this calculation that purification, full purification should be reached also in this limit of very weak measurements. However, the time scale that you need to purify your initial maximum mixed state now is exponentially large in the Fock space, in the number of particles. So it scales with Fock space dimension, and it's independent of your interaction strengths. So now with this we can compare our.
Tobias, just a question. These measurements that you are doing are projective in the sense that they p square is equal p.
Yes, exactly.
So you are not doing that special kind of measurement.
No, this is just like if you think you project like your local spin onto the z component or minus z component. Yeah.
Okay.
Yeah, exactly. So this is now what we find. So first we ran the simulation. So this is now for ratios of j and eta, where eta is 1/100th of j of the order. And first, what we see that's, I think, quite nice is that if we scale, so this is for different system sizes and the same ratio of j and eta. So if we scale these curves by our predicted relevant time scale for the purification, we see that the numerical data for the different system sizes collapse onto one universal curve, which is nice because it says that this time scale actually should be the relevant that we find. However, we see that while, so the analytic prediction would be the solid line, we see that this works quite well in the beginning, but then we see deviations of, let's say, 20% in the purity. And well, we think that probably this, or we trace this at least back to the to this uncontrolled approximation that we do. But what this gets right is again, as said, the time scale for the purification. So we find that the system purifies, but the time scale is exponentially large in the number of particles. And this again shows the deviation, or how the purification or the purity approaches one on long time scales. And one sees this follows again this exponential law predicted with TP, now the J independent time scale that scales with D. So that nicely is reproduced by this calculation. And here's now shown the numerical simulation for the same system size and different ratios of J and eta. And we see if J is, let's say, 20 times eta or larger, all the points here fall then onto the same curve, confirming the J independence of the relevant timescale for purification. So this is then what we arrive at from studying these two limits. So we predict purification will always happen in these mesoscopic systems. However, the time scale on which purification happens is quite drastically different. So in the weak measurement limit, it's actually exponentially in the number of particles, while in the strong measurement limit, it scales with log n. So what we then did here is we ran just some numerics for different system sizes n and for different ratios j over eta, and we tried then to see how these predictions for the typical timescale for purification match the prediction. So what we said is, let's say the typical timescale for purification is defined by when the purity reaches 90% of 9, when it's 0.9. And from this, we can then extract always the purification time for a given ratio j to eta and a given system size n. And for a given ratio j to eta, we can then see how the timescale for purification behaves in n. And what we find is that, well, the predictions for strong and weak measurements, they actually describe quite well a very broad range of ratios j to eta. So the weak measurement regime, which would correspond to purification time scaling exponentially with system size, is describes well the numerical simulations for j's being larger than 5 eta, and reversely, the results where we predict logarithmic in n increase of the timescale for purification describes well the data for j's below than 0. Eta. In between, then the transition happens, and specifically for j equals eta, we find that the typical timescale for purification actually scales with n squared. So now from these quite stability of the limits, let's say, of the weak and strong measurement regimes, then we try to make some more, to learn something more about the transition. And this is now done using, built on an effective Hamiltonian, which uses this stochastic Schrödinger equation with the continuous measurements. So again, there's some approximations here involved, which are in a way better or not well understood. So let me just briefly point out what we do. So we start out from the stochastic Schrödinger equation of the measured SYK model. And well, better we start out from the mass equation for the density of matrix. Then there's the first approximation, which is that we think, well, the measurements themselves introduce quite a bit of decoherence, so it should be fine if we project the density matrix on the diagonal components. So the coherence is stored in the off-diagonal element should actually decohere quite quickly. So we make a projection. So that's the first approximation that we do. Then there's one specific thing of the theory, as already said, like the density matrix itself doesn't store the information on the purification dynamics. You have to go to higher moments, like the second moment in the case of the purity, which means that for our theoretical description, we want to look at the replicated theory, which allows us simpler to address these higher moments of the density matrix. So we introduce in general some R-fold tensor product, R-fold replicated theory, which would allow us to calculate the rth moment of the density matrix. And then what we want to talk about is not the evolution along one specific quantum trajectory, but we want to have an average theory. So we want to average over all possible measurement outcomes, about average over the measurement noise. So our effective theory will describe the average probability of this replicated probability. And then there's one more approximation, which at least our collaborators, which have more information or understand this better, they're quite sure that this is fine in the weak measurement regime, which is to neglect the expectation value. So this is, again, because we do not know how to do it better. This expectation value introduces its nonlinear feedback, and that's very hard to take into account. So from their experience, it seems that in the weak measurement limit, that should be fine to do, and that's actually fine. It probably also gives you the right, or hopefully also gives you the right description of qualitative properties for the transition. Now, what we confirmed, though, is that neglecting the expectation values gives you parametrically wrong results for example, the purification time in the strong measurement regime. But okay, for the weak measurement, it should be fine. And then after these approximations, what we can write down is the dynamical equation for this replicated average probability, which takes the form of this imaginary time Schrödinger equation with an Hamilton operator given by these two contributions, and which can be viewed as the Hamilton operator of an R-legged spin ladder. So R here corresponds to the number of replicas. So for the purity, R would be 2, and it would be 2-legged ladder. So we have here, these are the different, let's say, replica channels, the different replicas. And then here is shown the sides 1 to n. And the effective Hamiltonian that now describes the average dynamics consists on the one hand of our SYK model that, as already said, introduces these 4 spin flips. And this part of the Hamiltonian actually wants to align all spins in a given replica channel in the same x direction. So it wants to point log all spins to be plus x or to be minus x. So that's what the chaotic dynamics does in this effective description. And in the average theory, the measurement itself now introduces a ferromagnetic coupling on every side between the different spins corresponding to the different replica channels. So introduces a ferromagnetic correlation, which wants on every side have all spins pointing in the same z direction in all the replica channels. And it can be, again, spin up or spin down. So these are the two competing mechanisms in this effective Hamiltonian description, which cause either this weak measurement or the strong measurement regime. And well, we can formalize a little bit the symmetry. So we can say that this Hamiltonian has a z2 to the r times the z2 to the n symmetry. So the z2 to the r comes from this invariance of flipping sigma x to minus sigma x in this Hamiltonian on all sides simultaneously, but it can happen differently in the different replica channels. So that's why it scales with R. In contrast, the measurement, the flipping of all sigma z to minus sigma z and all replica channels simultaneously, but on every side independently, gives you rise to a z2 to the n symmetry. So overall, one can see, for example, that looking at the unitary operator defined as a product of all sigma z operators on every side in the same spin, channel A. So if you multiply this from the left and the right of the Hamiltonian, that won't change the measurement operator and will flip the sigma x to minus sigma x. But since this happens on 4 operators, it doesn't change the Hamiltonian. So that's an invariance of this Hamiltonian. And this is actually related to a fermion parity that you have in the original SYK model, and that is here now popping up as a power of R because we have a replicated theory, and the d2 to the n is due to the equivalence of all the possible 2 to the n measurement outcomes. Now, in the long time limit, we can then use the Hamilton operator approach to look at the ground state. So in the long time limit, only the ground state should matter. So I said in the weak measurement limit, we find that the ground state wants to align all spins in a given replica channels, all pointing to sigma x or minus sigma x. So we have the z2 to the r different versions of that. While in the strongly measured phase, we want to have fully ferromagnetic correlations on a given site in all replica channels, which gives us this z2 to the n possible ground states. And then the observation is...
Just a question. Each one of the legs of this arm-legged ladder, they are different different states of your system. Your system is a single leg, right?
Yeah. So in the beginning, we start out with a single leg. That's the system. But then what we want to do is we want to describe rho squared in an efficient manner. So that's why we replicate the system, for example, to 2 legs, because this allows us nicely to describe rho squared just as it's a mathematical trick, right? You take the tensor product of the 2 systems, which then allows you to describe efficiently the dynamics of rho squared, right?
Okay.
So that's from the necessity that we cannot look at the dynamics only in terms of a single density matrix, but we have to look at higher moments. Only those encode information. And that's where the structure comes from.
But
then
if
actually,
no, sorry. If I wanted to simulate the system,
yes.
it would be one-dimensional. It would
Yes.
not be many legs. Okay.
No,
so the legs are just replicas, really.
Replicas.
Okay.
The replicas, and then something usual like happens is like what people from disordered systems know is like all the replicas see the same measurement noise, right? So that's why after looking at the average theory, you introduce then correlations between the different replicas. So the SYK model itself doesn't have any correlations between the different replicas, but due to the average over the measurement outcome, you introduce then correlations between these replicas, which is this ferromagnetic coupling here. So that's something for people who are working with disordered system, that's very usual, where the disorder would introduce correlation between replicas.
Okay, thank you.
Okay, so then the observation is to actually flip like such a sigma x polarized state in a given replica channel to the opposite. You would have to apply order n measurements, which means that that's very hard to do. So after the system has decided to go into one of these ground states, this is robust and should be stable. So in the weak measurement limit, then assuming one of these ground states, replica symmetry Z2 to the R should be broken. On the other hand, if you look at these ground states in the strong measurement limit, like for R equals 2, you need only 2 operators to change from the up polarized to the down polarized state. So this is very readily done, meaning that if we crank up a little bit the interaction, then we expect actually that not one ground state is chosen, but there's transitions happening between all possible ground states, meaning that in the end you will end up with an equal weight superposition of all possible ground states, meaning that in the strong measurement phase, then the full symmetry should be preserved. So from this, we would identify the transition from the strong to the weak measurement regime with replica symmetry breaking. And then one can also just calculate the energies of the corresponding candidates for the ground states. And then comparing, these energies, one sees that, well, the one ground state crosses over into the other true ground state at a scale which then we would identify with the scale at which the transition take place. And from this estimate or from this calculation, we would identify that at J equals to 2 eta, the purification transition should take place, which is actually quite reasonable agreement with the simulations. Okay, so with this, come to the summary and outlook. So I reported on our attempts to understand the dynamics of the measured SYK model. So in the beginning, actually thought that we could understand everything from this replicated effective Hamiltonian, and it was in a way a little bit of a hard lesson for us that the problem is more complicated than we thought. So we had to resort to this, let's call it, 3-pronged approach to address the different regimes. But okay, we have understood, I think, interesting things. Well, okay, we have understood some things about these problems, but there's some open ends where we would like, of course, to make progress. Not sure how hard this will be or if you manage, but of course, in the end, what we would really like to have is the full theory. Maybe there's other ways where replicas are not readed and so on, but we would have at least also like to have a theory that also would predict, for example, the purification time scale at the crossover or at the transition to scale as n squared and so on. Okay, and with this, I thank for your attention.
Thank you very much, Tobias, for this very nice talk. So, questions, anyone? If you don't have a microphone, you can raise your hand. We have this feature now that I believe was not available before. So there is a little hand on the bottom of your screen if you want to ask a question. Edson is already back. Maybe Edson has a question. Maybe not. Well, I have a...
Antonio has...
Yeah, go ahead.
Just a question. I'm not from the field, so I might be making a very naive question. But how large has to be N to be a mesoscopic system?
Yeah, okay, that's actually a good question, right? So I mean, it depends a little bit how you define mesoscopic systems, right? I mean, like, let's say traditionally you would define it a little bit different. You would say it depends on the ratio of the coherence length and the system size. So that was when considered single particle systems. So here I wouldn't give like for this many body systems, I wouldn't give a strong like definition, but I would say, so what you want to have is you want to have many particles such that, like what we used in the end, right? We used that you have enough particles such that the system is complex enough that you always have chaos, right? And then why we call it like mesoscopic, like if you would do now the limit n to infinity, of course, all these long time scales that we find would be completely irrelevant, right? They would be for n equals 100, I don't know, 1000 or whatever. I mean, this time scale for purification doesn't really play any role. So yeah, I mean, yeah. I don't know if this answers. I kind of I'm being very vague here, right? But so I would say what we are thinking about is really like a system that is very complex, that you have this many body chaos and so on. And now if it's like 20 particles or 50 or whatever, yeah. But it's like, I would say it's a kind of system that are simulated, right? Mm-hmm.
Yeah, I have a related question, because I was going to do the same question regarding n equal 10, because in the beginning you said n has to be much larger than 1, but finite. And right. I understand your point too, that n cannot be too large, or otherwise you lose sight of these times that you are looking. But from the point of view of someone who works with strongly correlated systems, right, it seems that n equal 10 is a small number. What is the difficulty of going to 20 or 25 or 32? Or you just wanted to stay at a small number?
No. I was just thinking about 10, because this would be like, well, you can go to 20, but that's the sizes that can be simulated, like usually, right? That are usually simulated. Let's say 10 to 20. Much larger will be complicated. And then also, like, if you think about what is currently done in the lab, you would also say of the order of, let's say, 10 to 100. Okay. 100 is already too ambitious.
Okay.
Yeah.
So that brings my second question. Can you simulate the system with cold atoms?
Well, what we really think is that, okay, so there's one thing that we did, which is considering the Majorana fermions, right? So in this way, we eliminate conservation laws like particle number conservation. Okay. Now, that's an interesting question, because if you have conservation laws, I mean, the system is not as good scrambling. You have, like, entanglement is inhibited by conservation laws, right? And there's actually something interesting happening, which is also called the sharpening transition. So there's subtleties happening when you have conservation laws. But okay, I would say that still, I mean, taking this caveat, that what we are discussing is very general, right? In the end, what we're discussing here is, as I said, like the SYK model, maybe you wanted to hear more about this, is like what people normally are interested in, is that it has like non-Fermi liquid behavior, right? Okay. So that's interesting. And this is killed if you would introduce this 2 Majorana fermion contribution. If the energy scale for the 2 Majorana fermion becomes comparable to the 4, then this non-Fermi liquid properties are killed and you have Fermi liquid. But all these things do not play any role. So actually we ran the simulations for the measurement. So in this sense, it's very robust, very universal. And given this, I would say that our analysis then should apply also to simulations or experiments that you could do in finite size, call them systems, apart from this conservation laws, which is one thing we should better understand. But I think this observation that you have two very different timescales for purification, that should be very robust, right?
Okay.
Yes.
Okay. Does anyone raise?
I do have a question. So, actually, I have two questions. The first one in connection with the previous question. So the difficulty that you experience when you simulate larger system, does it have to do with fast growing or entanglement entropy? Because typically when you simulate, you calculate time evolution of in the traditional monivariate system or I would say monivariate localized system.
Yeah.
So in the thermal phase, you have a fast growing entropy.
So in the thermal phase, you have a lot of entanglement, and this is why you cannot. I mean, if you are in the area law, you can use efficient like matrix product states or whatever to simulate, right? But this fails once you go to the thermal phase because you have more entanglement, right? Yeah, that's true. Yeah. So
the same thing happened here.
Yes, so I think it's just a generic thing of this chaotic regimes, right? That I mean, it's in a way it simplifies. Like if you go to the extreme limit, you see like if you're in the fully like information scrambling long time scales and so on, then in the end the dynamics becomes again very simple, at least here, right? Because I mean, you can model your evolution by random unitaries, but to get the crossover or the transition exactly right, if you go like above the transition and so on, that's very hard. Also, I think to then like if you would like to simulate this, I mean for the SYK model, you cannot go to more than what is it 20 now Majorana or complex fermions, to like 2025 or whatever, yeah. So that's a problem that you face in the numerical simulations, right? I mean, our analysis doesn't really depend, like what we did doesn't depend on, you could take n very large, but it was more the point about like that in these, let's say, mesoscopic size system, the purification also happens if d is not, I mean, astronomically large, right? Yeah, and you have these two regimes separated by the different timescales. Yeah.
Okay. My second question is how do you compare these kind of stochastic dynamics, so to speak, as compared with the traditional disordered model, for instance? In that case, your couplings your couplings are random, but now your measurement is random.
Right.
So, what the main difference and main similarity? Could you
yes.
elaborate on that?
Yeah. So we thought, like in a way, you could think that. So what we are interested in is these ergodicity transitions in many-body systems. Now we know the many-body localization problem is really hard. So what you think is, let's try to come up with some simpler variant. I think that was one of the motivations for the measurement transitions, at least like why we got interested in, because you think that should actually simplify things, because the measurement like introduces measurement noise, which leads to decoherence and so on. So the projection onto diagonal matrix elements, so forgetting about coherences and so on, should be doable, and this should actually simplify the thing. So that's one of the big motivations, right? You think it's more in this sense more classical in a way, like that you can forget about coherence, and this should simplify the problem. And we thought that maybe we could come up with a good description, but it turned out that in the end there's other things that become complicated. Like if you want to, like these projective measurements, you can nicely simulate on the computer and so on. But if you want to try to find a good analytic description, it's good to think about these continuous measurements. But then you have this nonlinear feedback, which is again a problem. So yeah. So in the beginning, the naive thing was measurements should be easier because coherences can be neglected and so on. But in the end, there's other problems appearing. Yeah, that's how I see it. Yeah.
My next question, George, I promise. So your dynamic does not depend on the initial state. You can start measuring at any initial state.
Right. I mean, the maximum mixed is in a way the most interesting because we know that, or we learned that the system is purifying in the end. So let's start with with the maximally mixed state to see then the full. I mean, let's start with the extreme opposite of a pure state, which is the maximally mixed. Yeah, but you could start with. Okay.
I have a very easy question. I could go to Wikipedia, but I am a bit lazy.
What? I won't know the answer.
So what does the letters S, Y, and K mean?
Oh, it's Sashdev Ye Kitaev.
Okay, yeah, that's true.
So the story is that Sashdev and Ye had some work in the 90s on spin systems and so on. Okay. So then I think Kitaev called it the Sashdev-Ye model, and since he gave the revival recently, it's now called the Sashdev-Ye Kitaev.
Okay. Yeah, I had seen that somewhere a long time ago, and I forgot. Yeah.
I think Kitaev came into the field in the early 2000s, right?
Say that again. Are you talking to Tobias?
Yeah, Kitaev came into the field early 2000, I guess.
Yes, early 2000. Yes. Mm-hmm. Yeah, and the original work by Sashdev, I think it's from the 90s. I think it's from the 90s. Yeah.
Okay, so thank you very much for the nice talk. I know a little bit more about the SYK model now.
Yeah.
Thank you very much. And we maybe